Welcome, my wonderful honor students. It's time for some good old-fashioned learning with Jockmans as we begin the second semester. We're going to first talk about the ideas of gravitation. For this video, which will take about 9 minutes or so, I really need you to have your classwork notebook open. Take some notes with me. Also have a graphing calculator, or the calculator you use normally in class. Because of the weird numbers of what's involved here, I'm going to kind of teach you how to use your calculator to actually calculate these very large numbers. So make sure you have it nearby. You're also going to be doing 2 examples for me by pausing the video. So here we go. The major idea we talked about, and we're going to continue to talk about, is the idea of gravitation. There are 5 key ideas. The first one, every object with a mass has a gravitational field around it. So anything with mass, whether it's an atom, a pencil, a planet, or a star, it has this field around it which is gravitational. When another mass is in that field, there's an attractive force between them. So since you're in the sun's gravitational field, there's an attraction between you and the sun. Since you're close to your pencil or pen, there's a gravitational attraction between you and the pencil or pen. The further the distance between the objects, the weaker the field, which means the weaker the force. So because I'm super far away from the sun, there's much less of an attraction between me and the sun than if I was really closer, let's say near Venus or Mercury. The farther you are from your pencil, the less gravity there is between the two of you, because there's less field means less force. The more mass that either object has, the more there's interaction in the field, which means the stronger the field, which means the stronger the force. So if you replace that pencil and you look at the pencil and now you put 2 pencils there, it's like it's a bigger mass overall, there's twice so much attraction. The more mass of either object, the more attraction there is. And finally, point 5, we're going to assume that objects are like single points of mass. So for example, if these are 2 planets, it's like we're going to imagine them as just itty-bitty individual points containing all the mass with a distance between them. We're going to ignore the fact that they are distributed over this bigger area. So when we talk about you as a person and your gravitational field, it's like we're imagining you're a single atom right in the middle of your body, and that atom has all the mass that you normally have as a person. It makes life a lot easier in terms of calculations. So there's 2 ways to use this. The first way to use is to find the amount of force, like get a number. How much attraction is there? How much gravity is there between them? Remember, when I say gravity, I don't mean the acceleration. I mean like the actual force, which is what we call weight. Mathematically, we have this equation. The attractive force, called F of G, is equal to this big G, m1, m2 over d squared. When I say attractive force, if it was between you and the Earth, we would call it weight. If it's between you and something that's not the Earth, we just call it the attractive force. Big G is this universal constant of 6.67 times 10 to the minus 11. It is just a number that makes our equations work with the units we chose. M1 and M2 are both masses. Now, very specifically, M1 is the mass that's making the field. It's called the object mass in kilograms. M2 is the mass experiencing the field of M1. It's called the test mass in kilograms. So for example, if you are near another person, you make a field that they experience, they make a field you experience. If we're trying to find the attraction between you and them, we could say that you're the one making the field, they're the one experiencing it, so you're the object mass, they're the test mass. And finally, D is the distance between the object and test mass in meters. As always, I'm going too fast. You can pause, rewind, do what you need. So let's do an example. Here are 2 planets. Planet A, 7 times 10 to the 22nd kilograms. Planet B, 6 times 10 to the 21st kilograms. They're separated by 7,410,000 kilometers. We're going to figure out how much gravitational force there is between A and B. Now that you wrote that down, when I say how much, I mean the amount of. When I say gravitational force, I mean that F of G, that attractive force. Between A and B, those are the 2 objects. Does it matter here if A is M1 or M2? No. The problem is not specific in terms of it. So we can call either one of them the test or object mass. So mathematically, we're going to use this equation. Here's my major hint. Don't put it all in the calculator at once. Order of operations will make you cry. Do the bottom first, and then watch what I do. I am sick and tired of students who know what's going on, that because they put all in the calculator at once, order of operations, they end up with a wrong answer, and I got to give them half credit or less because they don't show their work on an examination. Not this year, my estudiantes. Heck no. So here's my setup. I put in big G as this number, M1, M2, and distance I have this. Notice I have it times 1,000 because I'm converting from kilometers to meters. I'm not doing that for masses because masses should be in kilograms, but distance should not be in kilometers. It should just be in meters. So there's a lot of exponents here, which is why we're going to do a special thing. To simplify, when I put the bottom squared in the calculator, I get 5.49 e, or times 10 to the 19th. So this is what we're going to work with. Break it down. Let's multiply the top together. 6.67, and instead of 10 to the, I'm going to do e. In your graphing calculator, that is the second button followed by the comma. If you do it right, you go to e. And then minus 11 times 7 times 10 to the 22nd. Second, again, e, second, comma. You should pop with a little e. And finally, 6, second, comma, e to 21st. Do this instead of the whole like times 10 to the caret thing, because again, if you do it wrong because of order of operations, you end up with the wrong number because the calculator does a very specific order of operations routine. It's best to be safe rather than sorry. Doing this whole shebang, I get this number, 2.8 times 2.8014 e to the 34th times 10 to the 34th. So I'm going to do this in the calculator one last time. However, I'm going to do it in a very specific way. Again, order of operations. When I divide two things with exponents, I always put parentheses in. Because if you do it in a wrong order of operations, it ends up being a different number. So I'm going to do again 2.8014, second comma to the 34th, divided by parenthesis 5.49, second comma, e to the 19th, end comma, end parenthesis, I'm sorry. This is what your calculator should show in blue. And you get 5.1 times 10 to the 14th newtons of attractive force, which is a really big force, but not really if you think about it. If you do F equals ma with that force and the masses, it's really tiny accelerations. Gravity is not that strong. So we're still in part one, the amount of force to get a number. I would like you to now pause in a little bit and try this example for me. A planet 4 times 10 to the 23rd kilograms creates a gravitational field felt by a 3,000 kilogram satellite. The satellite needs 90,000 newtons of attractive force to stay in orbit. How far from the center of the planet does it need to do this? I'd like you to first please pause the video and create your list of what the variables stand for. I'll wait. And I'm done waiting. Here's what I said. 90,000 newtons of attraction force, that's Fg. M1 is the thing making the field called the object. This is the planet because it's creating the field, which mass is 4 times 10 to the 23rd. The second mass is the testing, the thing in the field, experiencing the field. The word felt means it's the satellite, 3,000 kilograms. We're trying to find how far. How far is d? We don't know. And big G is still that 6.67 times 10 to the minus 11th. Can you now please put these in the equation? Don't solve it. Just put it in the equation. Should look like this. 90,000 in blue equals 6.67 times 10 to the minus 11. 4 times 10 to the 23rd. 3,000 divided by d squared. You can now try to solve for d squared. I have it down here. You can see I multiply both sides by d squared. Then I put it all in the calculator on the right, and I get this number. Divide by 90,000. And then I square root both sides. Can you please make sure you can do this in a calculator to confirm that you're good with this? It's now time for the second and final way we use gravitation in mathematics. And that's the idea of comparison. So far we have calculate how much attractive force there is. Now there's going to be calculate how the attractive force compares to another situation. Example, in a new star system, the star is 2 times as big as ours, and a planet 3 times that of Earth is found 2 times the distance from the star that the Earth is from the sun. Woo, that's a statement. How does the star-planet attraction compare to the Earth-Sun? Copy this down, pause the video, rewind it once or twice. And we're back. In a new star system, the star is 2 times as big as ours. Okay, so their star is twice as big as our star. A planet is 3 times that of Earth. So the planet is 3 times as big as ours, and it's found 2 times the distance away. Using this equation, what we're going to do instead is we're going to say how the objects compare. Big G, it hasn't changed. It's still the gravitational constant. There's no change in the new system. M1 is the object. We're going to say it's the sun. The sun is now twice what our sun was. M2 is the test, which is the Earth. So M2 is Earth. The planet is 3 times Earth, which is 3M2. D stands for the Earth-Sun distance. Theirs is 2 times the Earth-Sun distance. FG is the Earth-Sun attraction. We're trying to figure out how much X their Earth-Sun attraction is compared to ours. So this is our setup. Using this equation, we're going to put in these in for the variables. So big G will still say big G. M1 is now going to be 2M1. M2 is 3M2. D squared is going to be 2D quantity squared. And FG is going to be XFG. So I'm replacing the left hand symbols with the right hand. Using algebra, 2 times 3 is 6. I'm going to pull the 6 out. 2D squared is 4D squared. I'm going to pull the 4 out. Big G M1 M2 over D squared is the original force of gravity. So big G M1 M2 over D squared is still force of gravity. I can cancel out the force of gravity from both sides. And I get the X, or the proportion, is 6 force, or 3/2 or 1.5 times as big. So that star and planet are going to have 1.5 times as much attraction as the Earth and the Sun. Finally, can you please try this one? A person's next to a car and experiences attractive force. How much further from the car does a person 2/3 as big need to be to feel the same force? Can you please pause and create the table like I did with the variables on the left and with their changes on the right? I'll wait. I'm done waiting. Big G, still big G, there's no change. M1 is the object, which is the car that's making the field. It's still the same car, so it's M1, there's no change. M2 is a test, the person nearby. The person is 2/3 the mass of the original person. How much further? We're trying to find distance. Distance is the car of the person. It's now XD. And to feel the same force, that means FG, which is the car to person force, is still the same. So plugging in, I get FG, which is still FG, equals big G M1 2/3 M2 over XD quantity squared. I'm going to pull the 2/3 out. You can see right here. And XD squared is X squared D squared. So I have FG, which doesn't change, is equal to 2 big G M1 M2 over 3X squared D squared. It's like I'm just rearranging the multiplication. Big G M1 M2 over D squared is just FG. Okay, there we go. So I'm canceling. I get 1 on this side, and now it's just algebra. Multiply by 3, I get 3x. Multiply 3x squared, I'm sorry. I get 3x squared equals 2. X squared equals 2/3. Square root it. 0.816. So I need to be 0.816 meters away. I'm sorry, 0.816 times as far, which is closer, in order to feel the same force. You've just done 4 great examples for me. Come in with questions about this. I'm going to assume that you've seen this, and we're going to go into more details with some examples and other things in class. Take care. Have a good day.